Swayam Prabha. Digital India. Educated India.
Welcome back to the Structural Dynamics course. In the last week, we have learned how dynamic analysis is different from static analysis. We learned how to formulate an equation of motion. We also learned the responses of free vibrations. We learned undamped and viscously damped free vibrations. So in this week, initially, we will solve a few example problems. After that, we will explore Coulomb damped free vibrations. Later, we will learn forced vibrations. So now, let's move on to example problems. Now let's formulate the equation of motion of this system. We have a mass, a damper and a spring. A dynamic force Pt is acting on this mass. So, for this system, because of the self-weight, the system will have a static displacement. So, the displaced configuration of this system under its own weight is this. dst is the static displacement of this system, and x is the displacement of this mass relative to its static equilibrium position. xt is the total displacement of this mass. So, xt will be equal to x plus dst. Now let's draw the free body diagram of this mass. So, a dynamic force Pt is acting downwards. Weight of the system is equal to mass times gravitational acceleration is also acting downwards. The damping force is acting upwards and it is equal to c times x dot t, the total velocity. And we also have a spring force which is equal to k times xt. So k times x plus dst. So now we can write the total force acting on this body in vertical direction. So the unbalanced force in vertical direction is equal to Pt plus weight, that is mg, minus kx minus kdst minus cx dot t, and this sum is equal to mass times the acceleration of this body, the total acceleration. So we also know that mg, that is the weight of the body, is equal to k times the static displacement, and we can find out from this relation that x double dot t will be equal to x double dot, because dst is a static displacement. This does not vary with time. And also we have x dot t would be equal to x dot. So we can rewrite this equation like this: mx double dot plus cx dot plus kx is equal to pt. So mg and minus kdst cancel out and we have this equation of motion. So if you look at this equation of motion, this is in terms of x and its derivative. So that means x is the displacement of this mass relative to its static equilibrium position. So if you write the equation of motion relative to the static equilibrium position, we will not have any weight term in the equation of motion. Now let's look into another system and write the equation of motion. The next system has a lumped mass m and a stiffener K. This does not have any damping, and the system is affected by a ground displacement xg. The displacement of this mass relative to the support is indicated as x, and the total displacement of this mass is indicated as xt. So we know that xt is equal to x plus xg. Now let's write the equation of motion. So if you consider this mass, there's only a spring force acting on the mass. So if x is considered positive in that direction, so the spring force will be in this direction. So it will be minus kxt. So that is the force acting on this mass, and this should be equal to mass times acceleration. So that is given by Newton's law. So this is our equation of motion. We can rearrange the term. It becomes mx double dot t plus kx is equal to 0. We know that xt is x plus xg. So we can expand this term. So we have mx double dot plus kx is equal to minus m x double dot g, that is the ground acceleration. So the ground displacement at the support is equivalent to having an effective dynamic force acting on this mass, and the effective force is equal to minus mass times the ground acceleration. So this is how earthquake affects a structure. So earthquake is a ground acceleration or ground displacement. So that would be equivalent to having an external dynamic force on this mass, and the value of that force will be equal to minus mass times ground acceleration. The next example is of torsional vibration. So we have a rigid disk of mass m mounted on a flexible shaft. So this is a rigid disk which has a mass m, and it is mounted on this flexible shaft with diameter d. Neglecting the weight of the shaft and neglecting damping, derive the equation of free torsional vibration of the disk. The shear modulus of rigidity of the shaft is G. So we can neglect the damping in the system, and we can treat the shaft as massless. So this just offers some stiffness to the system, and the disk has some mass. So this is a undamped free vibration system. So here it is torsional vibration. So let's draw the free body diagram of this disk. So far we have been dealing with systems where the mass was lumped. It was concentrated. So this is an example where the mass is distributed. The disk has some dimensions, some radius and some thickness. So the mass will be equally distributed across this disk. So mass is distributed here. So let's go back to the free body diagram. So if theta is taken positive in this direction, we can write the restoring force. In this case, the restoring torque is equal to the torsional stiffness of this shaft multiplied by the angular displacement, that is this angle theta. So the value of this torsional stiffness of this shaft is equal to Gj by L. G is the shear modulus and L is the length, and J is the second moment of area. You would have learned this expressions in the mechanics of solids course. So the restoring torque can be expressed like this. So now we can write the equation of motion using Newton's second law, which says unbalanced force, in this case that is equal to the torque minus Fs, that should be equal to the inertia. So that is, if it was a translational displacement, this would have been equal to mass times translational acceleration. So here this is a distributed mass and we are also talking about angular displacement. So this will be, the unbalanced force will be equal to angular acceleration multiplied by I naught, which is the mass moment of inertia of this disk. So for disk like this, the mass moment of inertia is equal to m r square by 2, where r is the radius of the disk. So minus Fs is equal to mass moment of inertia times angular acceleration. So now let's see what is the value of this torque. So the torque Fs is equal to Gj by L, that is the torsional stiffness of this shaft, multiplied by the angular displacement, that is theta. J is the second moment of area, and for this shaft it is equal to pi d to the power 4 by 32. D is the diameter of this shaft. So now we can calculate this torque and the mass moment of inertia. We have the dimensions of this structure. So now we can write this equation of motion as I naught theta double dot plus G J by L theta is equal to 0. This is the equation of motion. We can substitute the value of mass moment of inertia and the second moment of area, and we get the expression for our equation of motion as this. Let's do one more example. In this example, an automobile is crudely idealized as a lumped mass m supported by a spring and a damper, and this automobile travels at a constant speed v over a road which has some roughness. So the roughness of this road can be expressed as a function of x, and x is the position of this vehicle on the road. So the roughness is represented by a function ugx. We have to derive the equation of motion of this system. So this single degree of freedom system is getting a ground displacement ug at each instant. As the vehicle is moving over this road, this ug changes. So this is equivalent to a displacement from the displacement of the support of this single degree of freedom system. So let's try to solve this. So we have this mass connected to the spring and the damper, and it moves with the speed v. So when it moves, it goes up and down, and that roughness is given as ugx. The displacement of this mass is represented by the variable ut. So that would be the total displacement of this mass, and the displacement of this mass relative to the base is ut minus ug. So the total displacement minus the displacement of the base. Now let's draw the free body diagram of this mass. So this is the mass. So when the mass is moved in this direction, there will be restoring force in the opposite direction. So we have spring force acting in this direction and damping force acting in this direction, and there will be inertia force also in this direction. So now let's write the equilibrium equation. So that would be inertia force plus spring force plus damping force is equal to 0. So what is inertia force? We have learned that inertia force is equal to mass times the acceleration of the mass. That is mass times ut double dot. This is the acceleration. Now let's see the damping force. So the damping coefficient is c. So damping force would be c multiplied by the velocity of this mass. So the velocity would be the velocity relative to the base. So that would be ut minus ug dot. The spring force would be k multiplied by the relative displacement. So that is ut minus ug, and that should be equal to 0. So now we can rearrange these terms. So m ut double dot plus c ut dot plus k ut is equal to, take these terms onto the right hand side. That would be c ug dot plus k ug, and it is given that ug is a function of x. And what is x? We know that this automobile is moving with a velocity v. So what will be the position of this velocity at each instant? That will be the velocity multiplied by the time. So we can replace this variable x by vt, that is velocity multiplied by time. So the right hand side becomes c ug dot vt, it's function of vt, and kug vt. So v is just a constant, so this equation will become cv ug dot, it will be a function of t, and k v ug t. So this is the equation of motion of this system. Now let's look into some free vibration examples. So in the first example, we have a wooden block connected to a spring, and a bullet is fired into this block. The bullet has some mass and velocity. This bullet gets embedded into this block. We have to find out the resulting motion of the block. So what happens when this bullet gets fired into this block? So the bullet was traveling with some velocity and it has a mass. So when it hits this wooden block, both the masses, they will move together with some new velocity. So by firing a bullet which has some mass into this wooden block means we are giving some initial velocity to this wooden block. We will find out how much is the initial velocity, and using that we have to find out the resulting motion of this block. So let's see how to solve this. So in this question, the weight of the block is given, weight of the bullet is given, the stiffness of the spring and the velocity of the bullet are also given. Now let's calculate. The mass of the block is calculated as the weight which is given divided by gravitational acceleration. So we'll get the mass, and the mass of the bullet is also found like this. Weight is given divided by g, you get m naught, and stiffness is already given. So now we have to find out the initial velocity of the block. So how will we calculate it? We can do that using the conservation of momentum. So the momentum of the system before and after the impact should be same. So before the impact, only the bullet was moving with some velocity v naught. So the momentum is equal to m naught v naught, and that should be equal to the momentum after impact. So after impact, this mass gets embedded into it. So the total mass will be m plus m naught, and it will move with a new velocity u dot naught. So we can find out what is that initial velocity. So that would be m naught v naught by the total mass. So if you solve this, you will get the initial velocity. So after the impact, the mass of our system changes. The mass becomes m plus m naught, and the stiffness of the spring does not change. It is same as the previous. So we can calculate the natural frequency as root of k by the new mass, that is m plus m naught. And we just calculated the initial condition. The initial velocity we just calculated. Initial velocity is this much. Do this. And the initial displacement of the system, of the wooden block, was 0. So the initial displacement is 0. So using these two initial conditions, we can calculate the resultant motion of the wooden block, that is ut is equal to u naught dot by omega n sine omega n t. We know that for this free vibration, the response is of the form a cos omega n t plus b sine omega n t. And if we use the initial conditions, we can find out a and b, and a is equal to the initial displacement. Here the initial displacement was 0, so we don't have that cos omega n t term. So the total response is equivalent to b, that is u naught dot by omega n sine omega n t. So we can substitute these values and write the resultant motion of the block in this format. That would be in the unit inches. In the next example, we have a packaging with an instrument inside it. So this is an instrument and it is packed in a box, and this instrument with this mass m is restrained by springs of total stiffness k by 2. So there is one string of k by 2 stiffness above this instrument and another one below this instrument. And mass of the instrument and the stiffness of the springs are given. And this box, this container, is accidentally dropped from a height of 3 feet above the ground. So this box was dropped from 3 feet. So we have to calculate a few parameters of this system. So first, let's calculate the initial displacement and velocity of this system. So when this mass is supported by the springs, because of the weight, this spring will get compressed a little and this spring will get extended by some amount, and that would be proportional to the weight of this mass, weight of this instrument. So how much that deflection would be, the static deflection, that we can calculate by the formula mg, that is the weight of the instrument, divided by the stiffness. So we can calculate that static deflection. So that would be the initial displacement of this system when this gets dropped. So the initial displacement, that is u naught, is equal to mg by k. We can calculate the value of it. Now, what will be the initial velocity? So this package is dropped from a height. So when it was before dropping, it had some potential energy. So when it is being dropped, that potential energy will become converted to kinetic energy. So this will get some velocity. So we have learned in previous courses that velocity will be equal to minus root 2gh. The potential energy before dropping is mgh, and that will be converted to kinetic energy. So that is half mv square. So if you solve it, we can find this expression for the velocity. So using this value, you can calculate the initial velocity. So now let's calculate the natural frequency. The stiffness is given and the mass is also given. So natural frequency is equal to root of k by mass. So that is kg by weight. So you can calculate this value as well. Next, we will calculate the deformation of this system. So you know the initial conditions, we know the natural frequency. So you can calculate the displacement as a cos omega nt plus b sine omega t. All these values are known, so you can substitute and get the expression for the displacement of the instrument. And you can calculate the maximum deformation as square root of this term square plus this term square. So you can calculate the maximum deformation of the instrument inside the package. So if we know the maximum deformation, we can also calculate the maximum velocity or even maximum acceleration. So let's calculate maximum acceleration. So if this is the displacement, what is the acceleration? If you differentiate it twice, you will get acceleration. So if you differentiate it twice, what will happen? You'll get a similar expression with omega n square also as a coefficient. So maximum acceleration is equal to the maximum displacement multiplied by omega n square. We know the value of omega n, so we can find the maximum acceleration as well. Just substitute the value and get the acceleration of the instrument. Now let's move on to damped free vibration examples. The stiffness and damping properties of a mass spring damper system are to be determined by a free vibration test. The mass is given as m is equal to 0.1 pound second square per inch. In this test, the mass is displaced by 1 inch by a hydraulic jack and then suddenly released. At the end of the 20 complete cycles, the time is 3 seconds and the amplitude is 0.2 inches. Determine the stiffness and damping coefficients. So in this, the mass was displaced by 1 inch and then it was released. That means the initial displacement to the system is 1 inch and it was just released, the mass was just released, there was no impact or anything, so the initial velocity is 0. And we also know the amplitude of the motion at 20 cycles, and we also know the time taken for 20 cycles. So we can calculate the damping ratio and natural frequencies. We learned about logarithmic decrement. So what is logarithmic decrement? It is the natural logarithm of the ratio of amplitudes at different cycles divided by the number of cycles. So this is the logarithmic decrement, and the damping ratio zeta can be calculated as 1 by 2 pi of logarithmic decrement, and this is valid when the damping ratio is very small. If the damping ratio is very high, we have to consider the square root of 1 minus eta squared term as well. But if the damping ratio is small, we can calculate it like this. So here we know 1 by 2 pi, j is equal to 20 here. So we can take j as 20 because we know the information at the first cycle and after 20 cycles. So u1 is equal to our initial displacement because that is the amplitude of the first cycle, and uj plus 1 is the amplitude after 20 cycles, that is given as 0.2. So you can calculate the value of zeta, and we get it as 0.0128, that is 1.28 percentage. So that is a very small damping. Since the damping is very small, the assumption that we made here to calculate this zeta is valid. So we assumed that damping is small, so it is actually small. So the assumption is correct. If it was not small, then we had to calculate it using the exact formula. So now we can calculate the natural frequency. So to do that, we will find out the natural period first. So this system is a mass spring damper system. So it will have a damped natural period. So we can calculate the damped natural period using the time taken for 20 cycles. So it is given that 3 seconds was the time taken for 20 complete cycles. So period is nothing but the time taken for one cycle. So the damped natural period would be 3 by 20, that is 0.15. And we just calculated the damping ratio and found that the damping is very less. So in such cases, we can consider that the natural period is equal to the damped natural period. So the natural period will also be equal to 0.15 seconds. So we can calculate the natural circular frequency omega n, that would be 2 pi by Tn. So 2 pi by 0.15 is equal to 41.89. Now we will try to find out the stiffness and the damping coefficients. So the natural frequency square is equal to k by m. So k is equal to omega n square m. So we know the natural frequency, we know the mass, so we can calculate the stiffness. And we know that the critical damping coefficient is equal to 2m omega n. So knowing omega n and the mass, we can calculate the critical damping coefficient. We know that the damping ratio zeta is equal to the damping coefficient divided by the critical damping coefficient. So the damping coefficient will be equal to zeta critical damping coefficient. So you have calculated the zeta already, and we can multiply it with the critical damping coefficient. We get the damping coefficient. So in the next problem, we have a machine weighing 250 pounds and is mounted on a supporting system consisting of 4 springs and 4 dampers. The vertical deflection of the support system under the weight of the machine is measured as 0.8 inches. The dampers are designed to reduce the amplitude of vertical vibration to 1/8 of the initial amplitude after 2 complete cycles of free vibration. Find the following properties of the system. The undamped natural frequency the damping ratio and the damped natural frequency. Comment on the effect of damping on natural frequency. So, it is given the weight of the system and it is also given the deflection of the supporting system under the weight. So, if you know the weight and the deflection, we can find the stiffness of the supporting system. So, the weight is the force acting on that springs. So, it is getting deflected because of this force. So, the stiffness is the force by deflection. So, the weight is 250 pounds. So, this would be 250 by the deflection given as 0.8. So, we can calculate the stiffness of the system. Weight is given, so we can calculate the mass of the system. So, mass is weight by gravitational acceleration. So, now we know the mass and the stiffness. So, we can calculate the natural frequency of the system, which is equal to square root of k by m. The next thing we have to find out is the damping ratio, and it is given the amplitudes of 2 cycles. Right? It is given that the dampers are designed to reduce the amplitude of vertical vibration to 1/8 of the initial amplitude. We can calculate the damping ratio using logarithmic decrement. So, as we assumed in the previous example, initially we can assume that the damping is small. So, we can equate the logarithmic decrement to 2j by theta. This is similar to what we did in the previous problem. And we know that the amplitude becomes 1/8 after 2 cycles. So, at the first cycle it is u0, after 2 cycles it is u0 by 8. So, logarithm of 8 is equal to 2 and j is equal to 2 because this amplitude is after 2 cycles, and pi theta, which gives the value of theta is equal to 0.165. That means 16.5%. So that is very high damping. So since this damping is very high, we cannot make this assumption as the damping is small. So now we will recalculate the value of theta using the exact expression for logarithmic decrement, that is 2j pi theta divided by square root of 1 minus theta square. So from this we can evaluate the value of theta solving this equation. So we get theta is equal to 0.163. If you solve the previous equation, we will get the value of theta. Now we have to calculate the natural frequency of the damped system. So that would be equal to omega n, that is the natural frequency, multiplied by square root of 1 minus theta square. So we can substitute the value of theta here and get the value of omega d. So how omega n is different from omega d? So this theta is not a very small value here. So this term is less than 1. So omega d will be less than omega n. So the damping decreases the natural frequency. So because of the damping, the frequency of the system decreases.